And this mapping is a little, great, thank you. This mapping is a little different from usual mappings because it's a mapping on the transformation function that you use. I mean, it's not that you just map one variable on the other directly, but you have a transformation that changes along the path. This is a little more complicated, so you have to always solve differential equation to do this, let's say, mapping. So it is, if you want me to give something positive, because I have myself written papers about it, so this is why Jose Daniel asked me to work about this, to talk about this. So I, of course, have to defend it somehow in front of the referees at least. And so, I mean, on one hand, it is in the family of statistical physics, in the spirit of statistical physics, aesthetics of statistical physics, to try to put many models into a single model. For instance, the n-vector model contains the self-avoiding walk, contains the Ising model, contains the XY model, contains the Heisenberg model, contains the spherical model, so all in the single model with a single parameter n. With a single parameter n. And the same, for instance, the Potts model, two-state Potts model, or the n-vector model, etc. So there are these model families which are patched together. And these, if you want, these 5 walks that you see here are all, let's say, very famous by themselves. They have all their whole own history. They have all the, each of them is a very important, let's say, statistical physics model. And to put them all together in a single family with a single parameter, which is directly related to the fractal dimension, this is aesthetically something very appealing. And this is why people have jumped on that and why the mathematicians have been so keen. And this is why also we have all these 3 Fields medals, but this is Fields medals, this is not Nobel Prizes, so this is mathematics. And so, as I had told you from the beginning, percolation is not only a physical model in statistical physics, but has an entire community of very good mathematicians that do proofs about the existence of PC and that do all sorts of interesting mappings. And this is in the same spirit. So this is just to motivate, if you try to motivate you to follow this kind of this story of SNE. So what I would like to start is to show you these equations. No, it should work. Yes. So what is the mapping about? It's a little complicated because it's not just a simple mapping. So we go from one half space into another half space. We have a transformation from the Z space into the omega space. We have here 2 spaces. Both are half spaces, and both are described by a complex number, so by C. So we want is like there's a C, and then we have here a transformation between the 2. So in this space, which I would take about now, here, this is the origin. Origin here, yes. And here in this space, we have now our 2-dimensional walk, which could be, for instance, the self-avoiding walk. This is the fractal path. And this one is mapped here onto the real axis of this other complex space. So this is what this mapping does. And if you map in this direction, you call it G. And if you map in that direction, back, I call F. Okay? So this is the story. Now, this G is not just a fixed mapping. This G makes an evolution. This is why it's called Straum-Loebner evolution. So the G, the mapping itself, depends on the parameterization of the path, which is time. So you go along the path, this you call time, and here you have now that both of these transformations depend on this time. So the mapping is not a fixed mapping between 2 models. It's a mapping which changes all the time according to this differential equation, which was first formulated by Loebner, beginning of the last century, 19-something, yes, 1930 or so, yes, and is actually rediscovered and reused by Schramm. in order to describe this kind of mapping. And this equation, as you see, is an equation for this function g, is driven by this parameter here, which is a function of t, which is actually this Brownian motion that I'm talking about. This is just a one-dimensional Brownian walk with a diffusion constant, which is here the square root of k, of kappa. Yes? So this is the story. And of course, this solution of this walk, this equation, has to be done discretely because we have everything we do is discrete. So our walks are just given by discrete points. And so we have this transformation from the walk to the path, and we have the transformation. Now, this is the transformation from the walk to the path. And then we have another transformation which goes back, which is a transformation from the path to the walk. And this transformation is called F. And here I show you. Sorry. Okay. So, sorry, first I should repeat something else, which is very important. The condition for all of this to work is that this path here, the fractal path, must fulfill conditions. It must be Markovian. That means it must only depend on the previous position, and it must be conformally invariant. And this conformally invariant story is something which is important in critical phenomena, because it has been proven already by, 50 years ago by the Russians, that critical points have a general, more general, say, symmetry than dilation symmetry or scale invariance. We discussed scale invariance before for fractals, etc. But in fact, the family of the group under which you are invariant is much larger. It's group, as I explained to you yesterday, is a family of transformations that so they include of under other, of course, dilatations and translations and rotations. So the purpose of doing it, mappings here, they must be conformal, and they must variance. And this condition of conformal invariance, theoretical, but if you want, this is the condition sine qua non. I mean, don't have conformal invariance, you don't even start to discuss. Typically, as let's say, to start to work like it should. Let me see. Maybe I should come here personally to. So, to Terco. No, it's okay. Yeah. So, which is the one that actually we are going to use because we have. We want to see if this path can map it. It's consistent. Now, at the back transformation, one has to solve these equations on the computer discretely. That has to find a discrete algorithm. And Kennedy. I will now. Yes, already in its discrete version. The position of in discrete, which I call omega gamma. So the gamma k is the time of pt, k is the index of the time, yeah? And so the gamma k are given, and I want to consider function. Yes, so it's two complex numbers, the old ones. That is this sorry. It's the opposite. So, Here. Uh-huh. So F goes from left to right. Left. Okay, sorry, this was a small confusion. Okay, so you see now the omega here and the Z are in this space here. So here, there's Z, and here you have omega. You construct now these omegas from here, they are supposed to live here. This F mapping from Z to omega by now applying on the gammas the function Fi. Yeah? But the point is that this function itself now changes at each iteration k. Yeah? So depends on the values of k. It is omega k. Okay, and so this is the and the obtained your omegas in one. This is a scalar, and the displacement is a scalar. The delta t, the delta x that you have each time step for your Brownian motion. Yeah? And so, of course, no. So, and this summer here, sum is the sum over all time. So this accumulated time, yes, individual time step that you add at each iteration. And here this individual displacement that you add at the case iteration. Here, that you do on the computer to solve probably T and UT is I'm obtaining the driving function need to my driving function did originates to G. What the G to this is Brownian motion. Or you use F. Here technically I go from the plot now displacement square against time, we'll get a straight line because it's Brownian motion. And this is what we're going to do numerically to check if really or the shortest path. Because if you look closely here on the first list, you will see there's no shortest path. So many things are missing. So we have to now check, are they, let's say, SLE. So this is going to be checked as subject. Okay. So, so this was clear. Here, then I can now show you what the procedure applied on, let's say, shade. So what I first have to do is I have to put my walk here into the right shape. And the shape I need for this walk is that it has to be a walk that goes from the origin to infinity. Okay? While the walk that I obtain on the computer on the square lattice is not going to the infinity, unfortunately. It's just this finite piece of walk in a finite system. And so I need to first do a transformation from this finite system on which I have produced my walk to a situation in which I have what is called a chordal situation, which I have a path that goes to infinity. And this is done by the so-called Schwarz-Christoffel mapping, which is itself a conformal transformation. So since I'm making conformal transformation, according to the theory, I don't change the properties of the system, and because it's invariant, as I said, and therefore I can do that. It's not a problem. And so this is done now numerically, but I will show you just in a flash how it is defined. So this is what the Schwarz-Christoffel mapping is about. It's a mapping from both directions, from this finite bounded system, general on a polygonal system. So this is general definition is you have a polygon like a square, and you map to the infinite half plane, and then you can see how the iso height and the height and longitudinal lines are transformed. You see, you get this kind of polar opening, and here you see now the mathematical description of the transformation, and these xk are the positions of these points here. Yeah? And so, I mean, I don't want to go in more detail. That you implement this on the computer, and then pass from one into the other, so that now the coordinates that were before will become some continuous, some real numbers. It doesn't matter. You have now x and y coordinates in real numbers, which are just complex numbers that you insert in this procedure called gamma. So these complex numbers are called then gamma. Yeah? And so after you've done this, now you can check what I said. You can now plot this u, or this displacement, as squared as function of time, and you obtain a beautiful straight line with a slope which corresponds to the diffusion constant, and which gives you a kappa of 1.69, for instance. No? So numerically, in this, sorry, I should now say, in this case, I've taken the watershed. So my first homework is to check if the watershed fulfills its SLE. So first I have to see if I can get consistency with this equation here, no? The fractal 1 plus kappa over 8. This was the crucial equation that we had. I remind you just that you don't forget. No, I'll go back again. Here, this is the equation that we have to check. We know what is the fractal dimension of the watershed, 1.22, and we have to see if this checks. No? By the way, everything I'm saying here only works in 2 dimensions. I repeat this again. Eh? I don't need to even think about 3 dimensions. It's only 2 dimensions. So this makes it even less useful, of course. Eh? So come back. So this is just now the overview. You see, this is the time that I just described before, where the individual time step is given by delta t by this imaginary part of the z. I mean, z is now this value in this space. No, this is omega. Sorry, this should be. I mean, sorry, the numbers are confused. But this is now in this space the mapped value on the real axis. Yes, and so this is the called Loebner time also. And this Loebner time is, as you see, fluctuating. So it's itself not discrete in like usually when we do random walks, we have a delta t that is constant, and the Loebner time is not. And this poses generally a problem with all this work that you have to be careful about, because your random walk now has random time steps and random positions. Yeah? And so if you want to compare to usual random walks, usually you have to force it to you have to discretize time. You take your walk, and then you look at the positions at discrete time steps, and then you have a walk in discrete time steps, which makes it much easier to use. So this is one simple program they have to add in this whole issue. Well, and then you see here, this was the displacement, and these are plot once against the other, and you see also that the distribution, the probability distribution, follows very nicely a Gaussian. So we have shown numerically that this works, but of course, this is just a necessary condition. Yeah? And what is also clear, as I showed, that we have checked that this kappa value is the same, gives you the right fractal dimension that we know. So this image shows that the watershed is a very good candidate to be SLE. And in particularly interesting, there's a value of kappa, which is smaller than anything that is on your list. Remember the list that we had went from 2 to 4. I mean, The 5 models that are mathematically proven are between 2 and 4. The 2 and 6. Now 6 was percolation, and 2 was the loopless random walk. So now we get something which is then there's and also one which is k equals 8, which is a piano curve, but not proven, but this is what everybody believes. Okay, so now I would like to make another check, namely, I would now like to show you what is the general check to see the necessary condition that any conformally invariant path must fulfill. And this was shown for the first time by Duplantier for the Coulomb gas. And it is a so-called winding number. So you have your path, and in every moment there is a certain direction where it moves. And when you go from one time step to the next time step, there is a change in that direction. There's a change in angle, yes, from here to here. So there is this angle, no? And now what you do is you sum up the angle from the beginning. This gives you, no, the angle, the actual angle, no, because sometimes it's positive, sometimes it's negative. And if now you plot, or if you now study the fluctuations of this angle, this cumulated angle, it fluctuates because I mean everything fluctuates here. It's a stochastic walk, né? Then it must fulfill the properties that you have first a constant, and then the size dependent is logarithmic with a prefactor of kappa over 4. And kappa is again the same kappa that we have discussed before, which is related to fractal dimension. And this property is very general. It's for every, I don't know any path that is conformally invariant that does not fulfill this property of the wind angle. So we do that now for the watershed. Yes, here in this plot, you see that here the square, the fluctuations, the square of the angle is plotted against the system size. And if you make this now a semi-log plot, I mean, if you make the scale here logarithmic, then you see beautiful straight line, and the slope is k over 4, 0.43, which gives you a k of 1.78, for instance. So this is the so-called winding angle test, which is very famous and which is easy to perform also. And then there is another test, which is a very stringent test, a very strong test for SLE, and which is related to the formula of Schramm. So Oded Schramm, who also made this, I mean, he was the Mr. guy from the Schramm, Löwner Schramm. Yes, some. A is just a number, a constant, yeah? So you can also make some discussion about this A, but this is maybe, I don't go about this. Okay, so yes, so I was talking about Schramm. So Schramm's most impressive contribution in this was actually to write a formula for the left passage probability. So what is the left passage probability here? You have a here your path, the fractal path, and you make now let's say a line. How you call this here? In the direction of here, this is the angle theta. So you take a line in the direction here, angle theta, and of distance r. And then you ask your question if the path is on the left, or on the right of this line. And the answer will depend on r and on phi, on the angle. I mean, if the angle becomes bigger and bigger, it will be more likely that the path will go out to the right. So clear. And what Schramm did, he proved that the probability for going to the left as function of r and sigma is given by this very complicated formula here, where gamma is the gamma function, and this here is a hypergeometric function. And the kappa appears here. You see the kappa is here. And the angle now is here. No? So this is not a trivial formula. it's not a trivial test either. So if you fulfill this formula or you don't fulfill this formula, that makes a difference. Okay? And so the test that you do is that you look at this quantity Q, which is the difference between what you obtain for the left passage probability, which is this one, and what you expect to find, which is the formula. And then you can plot this Q, this function, as function of kappa, which is done here. And you see this is a very, very fine scale, because here's 1.69, 1.673, 1.77, a fine scale. And you can see very nicely that there is a clear minimum of this function of the difference between our data and the expected data at a value of kappa of 1.73, which is now in very good agreement with the formula of the fractal dimension. So this makes us now feel very comfortable to claim that the watershed is fulfilling the SLE condition. Yes, everybody agrees that this is not such a simple test. And you see here also the deviations, you know, as function of the angle. This is now the angle, and this is now this difference between the Q, the difference between the two. You see it fluctuates around zero. There's a certain error. Okay, so this is a, yes, that's your question.
What does it mean to be to the left of the Q?
It is, you can, of course, the probability if you go to the right is just 1 minus to the left. So this just doesn't matter if you go to the left or to the right. So
this curve is to the right?
yes, to the right. I mean, it goes to infinity because the curve has to go to infinity. In the past, the line is like this, okay? Go to infinity if you want, okay? So you can, of course, it can depend on the radius, of course. But I mean, you look at a certain distance and say, no, this is my radius. And then you say, okay, from this up to here, yeah, it has gone to the right. And it's gone to infinity. I don't know where it is. I don't know. It's, yeah.
So it's not crossing, but in the evening, it is to the right.
It's right. It can cross many times before, but then what happens at the end? Yeah? Okay, any other question? No. And so what I did here for the watershed, I will now do also for the shortest path. Let's do this for the shortest path. So the shortest path, you remember, it was on the percolation cluster, this white or red line with a fractal dimension of now different, even smaller. Yeah. And then you can now do the same. You can now first look at the winding angle to see if you have a conformal invariance. And you see that there is very beautiful, let's say here you plot the square of the winding angle as function of the system size, logarithmically plotted. You get then here this logarithmic increase, and the slope gives you kappa. Then you can do this, oops, always happens. You can do the left passage probability. Yeah, left passage probability. No, this is not the driving function. So now here, what you do is you make them direct SLE. You just make the transformation, or the F transformation, and obtain the driving function directly, and then you check that the driving function has properties of a Brownian motion, that it is the fluctuations squared grow linearly with time, and the slope is again the diffusion constant. Okay, and finally, we can also look at the Markovian property, something we should not forget. The path should have also Markov property. So how do we check the Markovian property? We calculate the time correlation function of the displacement of this path, in this case of our, and then we drive the function, and then we look at the time decay of this correlation function. This is the correlation function as usually defined. And then you see that it decays very fast to zero, showing that there is no correlation in time. So Markov properties are also fulfilled. So we can also here we can claim that all the tests have been done. It is following the Markov. But now there comes a question. This is, let's say, another proposal for a PhD thesis, which is something that had never been done, which is what happens now if you study the watershed or the shortest path on a correlated landscape. I mean, which depends on the Hurst exponent. This we discussed yesterday. We discussed yesterday that if you look at the shortest path or at the watershed as function of the Hurst exponent, you obtain for every Hurst exponent a new set of exponents, a new fractal dimension, and a new, of course, hopefully also kappa. So this has never been tried. So this is something that, I mean, because you see how the shortest path depends on Hurst exponent. So if the fractal dimension depends on the Hurst exponent, then also in principle, if everything is conformally invariant, etc., or not, you don't know, has to be checked, né? Then yes, you have a new set of kappas. Okay, so this is the open question. Now I will do this actually question or answer this question for the classical perimeter of percolation clusters. So remember, we have touched this subject in the first lecture very briefly, namely that in 2 dimensions, the surface of the infinite cluster, of the incipient infinite cluster, which is the cluster at PC, the surface itself has a fractal dimension which is different from all the dimensions. Not like in 3 dimensions equal to the fractal dimension of the bulk. It is a new fractal dimension. Okay? And in fact, there exist 2 different fractal dimensions, namely the complete perimeter and the accessible perimeter. What the hell is that? So the complete perimeter is very easy to say what it is. It is just all the sites that are on the surface of the cluster. So here, for instance, well, it's not easy to see because the color is not, yeah, here you can see it. So it's the one that goes along the entire path, huh? Yes. And then if you want to calculate the fractal dimension, you use the so-called yardstick method. That means that you take a certain stick of a certain length, and then you approximate your path, yes, with this stick, like this. You put this stick, yes, on this path, and you count how many sticks you need. And then you plot the number of sticks as a function of the inverse size of the stick. You get a straight line, and this is fractal dimension. Okay, this is like all these calculations of fractal dimension, a simple thing. This is the so-called complete perimeter. So what you do is you take a point, you make a circle around this point of radius of the length of the yardstick, and you choose the first outcoming of this on this line along the first that you encounter from, if you want, from coming from the path. And the first one you take as your position where you now place your stick, and then you do the same thing you do here, a circle, and look for the one that is the next one, and you put it there, you look for the next. This is how to proceed. Yeah? So you look always for the one that is most on the right side. But now you might also decide, no, I don't want to have the one which is the first one. I want to have the last one. And when you do that, you get different stick positions, of course, because you jump over all this. If you take this one, then you have to go around. If you take this one, you jump over all this and you go straight here. No, okay. So taking this is the last one makes this path much shorter, and it makes it so much shorter that even its fractal dimension becomes smaller. Yes, and this path is called the accessible, because you cannot access it from outside if the channel is too narrow. Yes, but it's not this, because many people think that you have to take a fixed channel width that you jump over. This is not the case. I mean, you jump over, what you jump over depends on the size of your stick, of your yardstick. Okay, so this is the fine point that has to be taken into account when you want to calculate the fractal dimension of the complete and the accessible perimeter. And as I told you, for the classical percolation, both of these perimeter fractal dimensions are known exactly. Namely, the one was obtained by Saleur, which is the one of the accessible perimeter, which is equal to the one of the self-avoiding walk, which is equal to what is it again? of the complete perimeter hull, sometimes they call it the hull. This one has a factor 7.5. First exponents. This is for her. This one, which is the classical percolation. This is the same picture here as this one there. I think so. Anyway, anyway, this is the same thing as before. But now you have here the perimeter and the accessible perimeter for h equals 1/2, minus 1/2, minus 1/4, and 0. This is the Gaussian free field, you see? And they look different. I mean, this is certainly flatter than that one. And for this one also, we know exactly the Fractal dimension to be 3/2, 1.5. This goes back to Scott Sheffield and so anyway. So, but I want to know now if these paths are SLE. And so let's do the same test. As function of the Hurst exponent, the Fractal from 4/3 to 1/2, and it goes from 7. It has only one. Yes. You have a beautiful logarithmic, in the logarithmic scale, you have a logarithmic increase. Here, I show you how this is here from, and this is the omega space. I mean, this is the Brownian motion, and this is the original path. You can compare. You see, there is a difference. This is now for h equals 1. So this is the classical percolation case, yes, and this is more close to this Gaussian free field. Just to get a feeling how these things look like. And then you can, of course, analyze this more carefully, and you obtain for every value of h, you obtain a different slope in the diffusion constant in kappa, which shows that there's a continuous change of kappa as a function of h. And this is shown here. So this is first exponent. This is the kappa. You see kappa from 6, which was percolation. This was the price, the Smirnovs, etc. No, but this price here. And this is here 4, which is, as you know, yes, this was the work of Sheffield. So the endpoints are exact, and you have intermediate values. And here you compare now the values that you obtain from this direct SLE with the values that you obtain from the diffractal dimension, with the values that you obtain from the winding angle, and they all agree. So this gives you the feeling that indeed these are SLE. Yeah? We have now a continuous family going through this higher spectrum from D equals from K equals 6 to 4. And hello, yeah. And this is now the test of the Markov property. You see, this is the correlation function, this function of time for values of 3 different values of Hurst exponent. And you see for all cases, there is no correlation, and they follow Gaussian. So also this property is fulfilled. And now let us have a look here. So the accessible perimeter also fulfills number property. No, not so well. Let's see what, because now I have here in this case, no, it fulfills, really it does, but I have done something more. Now, also to positive 8. not was said, but before, I only looked at negative H. So what you see, positive ones. And what one finds is that, well, here, these numbers, later we'll see, are not coinciding. We'll see that. So these, so we have, you know, up to here, we have a set that goes from, what is, should not be kappa? Kappa, no, kappa. Kappa goes from, should go from 4 to 6. No, I don't know what's going on. Sorry. Unless it was different. No, sorry, it's not accessible. Accessible goes from to 2. Yeah? Okay. So this should be okay. This is no 8/3 to 4. 8/3 to 4. This is what it should be. So it does the right thing here. Yes. In the tendency. And now looking at the left passage probability. This remember this is a very fine test. You get very really here a small kappa value, which here you see now for different Hurst exponents. And here again, you see for different Hurst exponents and also the positive Hurst exponents. If I now compare, look at the values here are 2, 6, 3, 5, 3, 6. And if I go now back to the old one, here's 2, 6, 3, 5, 0.6. So between here, something doesn't work. Yeah? Here, everything seems consistent. And here, there is trouble. So you see, also, I show this because I want to show that it does not always work. I mean, there are cases where it does not work. And then the same, if I look at the direct SLE, means I make my transformation from the omega space to the Z, no, from the Z space to the omega space and obtain the Brownian motion. You see the Brownian motion is beautifully fulfilled for H Hurst values, which are negative. And you also have for positive ones, it also works. But the exponents, again, are different from the other ones. So if I now plot, and the Markovian property is very striking. You see here, this is the correlation function, the time correlation function for negative H and for positive H. So positive H have long-range time correlations. The Markovian property is violated. And if I now look at the exponents, you see this is now the Hurst exponent from -1 to +1. So here we have the negative ones up to here, and then I have the positive ones. And you can see that the negative ones, all the different ways to calculate the kappa diffusion are consistent, but when you come here, they separate. So here, there is no more consistency in the kappas from the different techniques. And this shows that, that here you have very good candidates for SLE, and here certainly there is no SLE. So this was particular to show the dependence on the Hurst exponent. Good, and now I will become very, very wicked, very strange, because I will now test this transformation, this Löwler transformation, out on paths which are clearly not conformally invariant. What do they produce? What is the effect of this transformation? Just to get a feeling of the transformation. And so what I will study now are 3 different kinds of, or 2 different kinds of anisotropic percolation. One of them is what is called multi-layered percolation. Multi-layered percolation is like this. You have here layers, layers. And then I do now say some layers have P a little larger and some layers have P a little smaller. So for half of the layers randomly chosen, I take P plus delta, and for the other half, I take P minus delta, which makes that if you look at these pictures, this is now typically such a cluster. There are a lot of occupied sites in the regions in which the P is large, and then there are empty regions where the P is small. And this is how the cluster looks like. So this is a zoom. This here is a zoom of that, just to see how it looks like. And so if one now does the direct SLE of this path, one obtains here this kind of curve. and we will analyze this curve a little bit. Yeah? But then also, this is one anisotropy in this direction. There's anisotropy. And then I will also look at our friend from yesterday, namely directed percolation. Directed percolation has an anisotropy in this direction. You remember, this is when you put the arrows. You have this. And then I will study now also the perimeter of directed percolation. This is just the outside perimeter. This is again a loopless path, which could be a candidate. In principle, it could be a candidate for SLE, but it is not. We know it is not because anisotropic models are not conformal invariant because they don't have, let's say, rotational or whatever symmetry. So I mean, there are some trivial symmetries are broken, and so it cannot be conformal invariant. So we know it does not work, but we can try what happens. And so you see, this is the typical path of the perimeter of the directed percolation. And this is zoom here for the region. And this is typically the driving function that you calculate applying the procedure that I have shown you already now several times. But I would like to show you now, this here. And now the result is the following. Result is that if you have an isotropy, oh la la, Olga, me puede. Meeting acabó. No, no. Aquí, ¿no? No, ok. No, está bien, está bien, está bien, está bien. Ya, está bien. Okay. Okay, okay. So, you know, I study the driving function. The driving function is supposed to be a Brownian motion. This is now the square of the displacement is function of time. And this is now a straight line with slope 1, which corresponds to classical percolation. This is the data for classical percolation, for the perimeter of the classical percolation cluster. And now what you see is this here is what you get for directed percolation. So this is another exponent because this is a log-log plot. So the slope here, 0.67, means that I have now a path that goes like this with alpha here being 0.67, which means that this is subdiffusive. It is not a Brownian motion anymore, it's a subdiffusive process. And if I do the other kind of anisotropy, namely the multi-layered, which is an anisotropy in this direction, then I get something which is super diffusive. It means where the exponent in the log-log plot is now larger than 1, is 1.78. So here alpha would be 1.78. So it's an interesting remark to see that, that if you generalize this whole concept of this mapping, that the anisotropy is reflected in super diffusive and subdiffusive walks, and maybe one can extend in that sense. This has not been done yet. I mean, from a theoretical point of view, this certainly means that you can extend this whole SLE theory in this direction. And one can also probe everything now opposite. One can say, what if I imagine I now put in a driving function which is correlated, long range correlated in time. That means which is a super diffusive or subdiffusive. And I then look what would be the corresponding fractal path. And this is what I show you now at the end here. This is first, I show you now how to make the numerically the solution of the function of the equation G. I will show this here in a minute. So you start now with the random motion that you have, I mean, the directed, whatever, sorry, with your driving function, yes? And you now apply on the driving function, this function G, and obtain now the gammas. So this is the inverse. And at the end, what you do is you look at the anisotropy of the walk that you create. And this is given by this expression. I will not talk too much in detail. Maybe how you make this is just the difference between the values of the path in different directions. And so what you find is that if you take a driving function, which is uncorrelated, like the Brownian motion, then you get a no anisotropy. If you take a driving path, which is persistent, that means that you have it's correlated, it is strongly correlated with the power law with an H exponent of 0.8, then you get a strong anisotropy in one direction. And if you take strongly anti-persistently correlated ones. That means that fluctuate anti-persistent, then you get anisotropic quarks in the other direction. So there's a clear, in both directions, a clear sign that the anisotropy plays a role in the hyperdiffusivity of the driving function. Okay, I don't know how much time, I've completely lost contact with time. I have, you must have a lot of time, yeah? 40 minutes, okay, so good. More, I have some time. Okay, good. So let's now come to my next subject, which is explosive percolation. Yes. So this whole story started with a science paper in this a few years ago, which claimed to find a first order phase transition in percolation, explosive. And this work, as I will show you in a minute, it was not right, but it was the motor for a whole evolution. They discussed this work. So this was the authors, Herrmann, Sousa, and Spencer. And the model is defined as the following. It's called the product rule. So these people were mathematicians. And so they started out with a fully connected graph. Instead of taking a square lattice, they took a fully connected graph. As I mentioned already yesterday, these fully connected graphs pose problems conceptually to define what is a spanning cluster. So anyway, but so what they did is the model is the following. Instead of, so this is, instead of taking like in classical percolation, you choose one bond and you occupy the bond or leave it empty. What you do in this product rule is you choose two bonds, and then you ask the question, which of the two bonds creates the smaller cluster? And you then only occupy that one. So the trick is to try to have not so many small clusters, or in other words, to have less large clusters in order to delay the transition. Yeah, instead of having very fast a large cluster, one has to try to keep the large cluster as small as possible, or in other words, to make the small clusters as large as possible in order to destroy this imparity. And what they find is that while the usual percolation, it looks like this. Yeah? This is the order parameter of the percolation, the density of sites in the infinite cluster. What they find is that it goes down very steeply. Yeah? And this is why they say, oh, we have a first order transition in the order parameter, yeah, jump. But this was not very convincing. Somehow already very soon, people saw that the cluster size distribution at this transition was had many clusters of different sizes. And if you analyze this in detail, you see that it's a Pauli distribution. So this is not very typical for first order transitions. This was very suspicious. And then finally, there were 3 papers that came out more or less also at the same time, kind of. One in Nature, one in Science, and one in Physical Letters by all these mathematically oriented people that were proving that you have to make systems of the size of several hundreds of millions of sites in order to be able to see that actually these transitions are continuous transitions. They are not further transitions, but they are actually, the whole story was wrong. And so in principle, you could forget and say, okay, this was an attempt that was failed. But this inspired other people, like for instance, this guy, to propose another model to say, why don't we not, instead of taking 2, we take now M bonds, and from M bonds, we select now the one which makes the smallest cluster. And then if you look now at M equals 10, yes, you do see now substantial differences from the previous cases. So this was classical percolation, the second moment, the order parameter. This was the M equals 2 model of Achyoptas et al., which was the, let's say, the one that was so destroyed by the end. And this had the same properties here, the same exponents, everything the same like in classical percolation. While if you make M equals 10, you have a different behavior, and order parameter falls down, and here the exponent increases to 2, which is the dimension of the system, which is what you expect for the first order transition. First order transition, the exponent should be integers equal to dimension. And this is what you see here. So this is very encouraging to say, oh, maybe m equals 10 is a candidate for really first order transition. But unfortunately, numerically, this was never was not possible to settle, because there was this kind of monster of these three mathematicians. And everybody was scared to death to say anything after that. So nobody was going to make any numerical statement after this kind of discovery. And so this remained open for a long time. And I'm sorry, I'm going the wrong direction. So today, at the end of the lecture, I will hopefully then be able to show you more convincingly what happens. So in the meantime, models were discussed, new models came up in the same spirit. The idea is always the same, is to suppress the largest cluster so to delay the transition. So now here we have a model in which you say that you select randomly a bond, like usually, and you occupy it unless it does relate to the largest cluster. So every bond you can place, except when it is connecting anything to the largest cluster. The largest cluster is special. The largest cluster, you have to make a procedure, namely you have to look at the size of the largest cluster minus the average size, take the square of this, and then minus the exponential. And then only occupy it with this probability. So the connections of anything to the largest cluster are strongly reduced, and they are the more reduced, the larger the cluster is with respect to the rest. So it becomes extremely difficult for the large cluster to grow. Everybody grows in the large cluster. Every time you want to grow the large cluster, then the probability to put the bond is very, 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 very small. Okay? So this model now has the property that indeed you have a very sharp transition in the order parameter, jump, as compared to classical percolation. And if you compare, this is the classical percolation. This is there. And you compare the distribution of cluster sizes, you find a bimodal distribution here in this model, which is, of course, what you expect for a first order transition, while in the classical percolation, you have a power law. So here, really, this has all the ingredients of first order transition. And when you look at the clusters at the transition point, yes, you find this. You find that the clusters are compact. They have no holes. Yeah? And they are big. They're all big. There are no small clusters. Let's compare this to classical percolation. This is how classical percolation looks at PC. And this is how this largest cluster model looks at PC. So clearly, this is not a critical point, because clearly here you have no power law distribution in the cluster sizes, and you have no fractality, or you have fractality? You have fractality. We have fractality in the surface. In the surface. And what I will show you over the time is that the fractal domain, that this fractal object here is nothing but a watershed. The watershed that we discussed yesterday, suddenly it comes up today again, namely here, in this model, as the surface of the compact clusters as the first order transition. Well, this is but of course, I just show you first just the numerical results. Sorry. Yeah, so the numerical, too fast, not too fast. So the numerical result you see here for this a similar model, two different models are similar, but the numerical results show that the fractal dimension is 1.22 or whatever, is very close to what we obtained in 2 dimensions for the watershed. Yes, so you can do everything also in 3 dimensions. Yes, this is now the 3-dimensional situation at the critical point for this largest cluster model. And this is classical percolation. You see there's a big difference. And you can then also study the surface fractality in 3 dimensions. And you find it agrees very well with the surface fractality, surface dimension of the watershed. So the 3-dimensional watershed appears. So Now, an even percolation model, which is percolation. So what is something very similar to a red is an empty bond. So it's like the last missing bond that you have to put to connect to the bridge. Scaling. So the model no chance to percolate. So this model is certainly not percolating because of P equals 1. Yeah, you topper, and this one. So these clusters, they go, and the red. So what you see here is that at the end of this line, forbidden bonds. Okay? And now is exactly the watershed. Because of first bond that we will one, then the second one, then the third one, and so on, according to some random choice. Random line with water. Yes. And then exactly flowing that you have of water that goes top for here are the green ones. The green ones are the bond to the north, and the blue ones are the bond. That's it. If you go back to the concept of today, if you and you kind of heights, you say what is the smallest height, the lowest, the second smallest. Yes, yes, yes. You imagine now, yes, and that the sites that you occupy first are the lowest ones. No, that you are just that you have just the landscape that you go as you fill with water. No, you just go from one to the next, the lowest one to the next lowest one, etc. You have the process that explained yesterday. Landscape with filled water. Height. It must, of course, level, height, level. Whenever the level of the water, its a position reaches the connection, then the water will flow out. Yeah. Okay. Good. Any other question? Has this been clear? I mean, the numerical evaluation, which then is 2 more or less. And now ridge bonds has a fractal dimension of 1 over nu, which is the fractal dimension of the cutting bonds, as proven by Corneliu in 88. It was exact. And so we know this. And then we evolve, and at the end, we come to the watershed, which we have just shown has a fractal dimension of 1.22. What happens? We can analyze this. What in the middle happens is that there's a crossover from this situation to this t equals 1. One looks already closely on this graph, you can see that these curve very fast and become asymptotically parallel to 1. Yes. So in fact, if you look at the numbers, you will see at the slopes, if you look how the slopes behave, yes, you will find that they produce for you an order parameter, which is the density of bridge points, yeah? bridge bonds. Yeah? This is the this here. Sorry, I must. This one is on top here. No. Okay, so this graph here, which is not shown, shows you how for different system sizes the number of bridge bonds increases when you go beyond the percolation threshold. Here we have chosen bond percolation on the square lattice, which has an exact PC at 1/2. This is why this is 1/2. Yeah? And so what you can see now is that you divide this curve, these values of the number of bridge bonds by the fractal dimension and plot it against P, then everything falls on a beautiful universal curve. And this universal curve has here a power law behavior with a square root. Here's a square root behavior, okay? And so you can put this behavior together into this kind of law. It's to say that the number of bridge points, bridge bonds scales with system size at PC, like the red bonds. And then there is a crossover to what happens at P equals 1 with a fractal dimension here of 1.22, which is watersheds. And this is the crossover exponent in P minus PC, which is just 1/2. Okay, so I've formulated a scaling law from the transition from one fractal dimension to the other, knowing that the dominant fractal dimension is the one from the watersheds. Yeah, and this, in fact, if you go even further in the let's say in the analysis of the criticality, to include the fact that this is also, let's say, a kind of yes, a critical point, a tri-critical point. In fact, you can formulate actually this also in such a form like this. This is the leading one, and then you have a theta, and this theta is given by that. So all this is called tri-critical scaling, and this is what you have in specific situations. This is very for specialists at the theta point. So don't worry too much. We only need this kind of relation in the future. So we need this because I will come back to that. So what we have found is, this is important to memorize, is that the number of bridge points scales like L to the fractal times P minus PC to some exponent. This fractal, this law, this scaling law, I will apply in a few minutes again. Okay, is this okay? Good. So in 3 dimensions, one obtains, of course, also a frontier between the 2 clusters in bridge. If you bridge percolation in 3 dimensions, you get again 2 clusters separated by a surface, which is again like the watershed. And if you go in higher dimensions, then you find, this is in 3 dimensions, you can do the same kind of tri-critical scaling, etc., but just with a different exponent. And then if you go to higher dimensions, this is now 2 dimensions, 3 dimensions, 4 dimensions, 5 dimensions, 6 dimensions. Remember, 6 dimensions is the end. Percolation, there's no more above 6 dimensions, the world is different. But what is interesting is that this watershed dimension goes from 1.22 to 6. So in 6 dimensions, the watershed is dense. That means the number of ridge bonds increases enormously with the dimension of the system. Because already in 3 dimensions, yes, the two clusters, I mean, they interpenetrate much more. In the higher dimension, the more the clusters interpenetrate. But then when you come to 6 dimensions, as I told you, suddenly you don't have one infinite cluster, but infinitely many infinite clusters, and you can connect any of them. You can make a kind of between them these kind of bridge bonds, and so above 6 dimensions, the watersheds remain always. They grow like this bare dimension of space. I mean, they grow. Nearly all sides are bridge bonds. Okay, so this is what happens with bridge bonds in higher dimensions. And now I will do the opposite just for fun. I will start with a fully occupied system and randomly remove with a condition that I'm not allowed to remove a cutting bond. No, the classical cutting bonds. And so if I do that, what happens? Well, the blue clusters are the ones that are separated from the boundaries. So up to now, everything is connected. There's some blue clusters appearing, you see. But then you see that these sides here are all the cutting bonds that you have not allowed to occupy. And if you analyze this curve, it again is like a watershed. But if you now go to higher dimensions, this problem is different. In higher dimensions, this line which remains here, this is here the remaining of the infinite cluster, because this model, you are not allowed to destroy the infinite cluster. So this is what remains from the infinite cluster. And you could, the first thing you thought, oh, what remains is probably the shortest path. No, it's the watershed for some reason. You know? Yeah, you could have think it's the shortest path. That's not. but then when you go to higher dimensions, it's not the shortest path. It's not the watershed anymore, but it is a set of paths become more and more one-dimensional, actually. So it's that since the duality of 2 dimensions plays a big role. Due to duality, the two problems, the cutting bonds and bridge bonds, are dual to each other, and so they give the same result. It's alarma. Simular, okay. So this is the story of the cutting bonds, yes. So now I come to my only science paper I made in my life. This is by for chance. This is now a paper, a model which combines these things. Namely, remember the first product rule model, we have to choose 2 of them, and then we say we choose the one which makes the smallest cluster. Now here we do the following. We choose M bonds, empty bonds, simultaneously we choose them, and we occupy any of them randomly, except if it's a bridge bond. We don't occupy bridge bonds, okay? But now comes the trick. We do occupy bridge bonds when there is no choice anymore. It means when all M bonds that I have chosen are bridge bonds, then I have to take one of them. So instead, as compared to the bridge percolation, in which at the end of the day, I cannot occupy a bond and I can never percolate. Here I do percolate. I do percolate when I have at the same time M bridge bonds. Okay? And then I have to choose one. So I do percolate. This makes the model even more rich. So here this is showing the case of Herrmann, but we have two bonds. If this is a bridge bond here, and this is not a bridge bond, then you occupy this one. But if both of them are bridge bonds, then you have no other choice, and you occupy this bridge bond, and then you percolate. Okay, so in this model, you find the following thing. Depending on M, this is now a different M. M equals 1 is just classical percolation, nothing different. And this is this per order parameter of classical percolation with beta equals to 5 over 18, everything known. Now, if I take M equals 2, I get this line here, a jump. I get equals 3, I get a jump, and I get hysteresis. So I meant when I come from here, I come and I go up here. And when I come from here, I go up here. And when I take M equals 4, I am here. So I go up here like this, up, and I go down like that. So we get beautiful first order type transitions in a finite system. Okay. But now what happens when the system changes? I mean, we have already learned from the past, from the work of the explosive percolation, Then we have to be very careful with these stories, with these sharp transitions as function of the system size. And so we will look at different sizes. And this is now what you see here. This is the sizes that were 2 orders of magnitude. What happens with these transitions? And you see this is now for different m. For as m equals 1, we have here, there is no change. This is 1/2 is the phase transition always. This is immutable because of that very strong result. But then, for instance, for m equals 2, my transition shifts slowly towards the classical one. So you can expect that for infinite systems, it will be just continuum percolation. And then for a very large, for 4, for instance, m equals 4 here, what happens is that my transition moves closer and closer to 1. And at the end, it becomes 1. So that might like the same as in bridge percolation, that you have essentially no transition because it's at 1. Yeah. But then there exists an MC somewhere in the middle, which does not change. I mean, this is, yeah, that's the point. And for every dimension, you have a certain value of MC. So this is in 2 dimensions. The value is about 2.55. I should say, in order to get non-integer values, one has to mix with certain probability. One does m equals 2, and with another probability, one does m equals 3. And then you can change this until you get 2.55. And here, this is in 3 dimensions, the critical number of bonds that makes your first transition, or is it 5.98? In 4 dimensions, it is 16, 17, kind of, yes. So you can calculate for every dimension numerically, which is the number of bonds that you have to choose in order that you get a first order transition. What's happening? See.
Pero era opcional, ¿no?
Eso es el jefe. No me mire a mí porque el jefe es él.
Vamos a acabar esta salud. Sí.
Pues vaya contando. 6, 10, 26, 27, 28, 29. Okay. So this is what you find. And now the beautiful thing is that one can harden this result, in fact, also analytically. Namely, by using now the scaling law that I discussed before. Namely, the criterion for percolation is that m bridge bonds simultaneously are bridge bonds. The m bonds are simultaneously bridge bonds. The probability that one bond is a bridge bond is the number of bridge bonds divided by the total number of empty bonds. And if you take this now to the power m, this is the probability to have m simultaneous bridge bonds. Yeah. So the probability, the criterion for percolation is now that this probability times the volume be 1. Perhaps the volume. So you have to multiply still by NB, which is the volume, which goes like L to the D. I mean, this D is because we have now bond percolation. So there's for every side there are D bonds. Okay. And so now I can replace this NBB by this scaling law, which we have derived before. This is what I did here. And I already replaced N to the D fractal. I replaced the L by NB to the 1 over D. So I have here NB to the D fractal over D. Okay. And if I put this out here, I get here minus, I could put this right, maybe. I hope I will. I get this right, so then I have here minus M. And then you have here plus m times d fractal over d. Okay? So this gives you here d fractal minus d over d times m. Yeah? And now this should, on the other side here, we would have then, or this should be, so we have then nb to the times q equals nb to the power of what? Of m? No, of m. Yeah, of m times df minus d over d. Yeah? And that means that at the end of the day, this is like 1. Yeah? Put this on the other side. The critical m equals d over d d minus df. So minus. Yeah? Okay. So this is a way to directly obtain now this relation here that I have numerically obtained of how the critical number of bonds depends on the dimension of the system. And one can even further, I mean, this is, was really a tour de force at the end. We can even prove that how if you are not at PMC, but you are above or below MC, how fast you are moving upwards or downwards in PC as function of system size. So here you have the law how P minus PC goes if you are above, below MC, and here is the same above PC. So you can find the full relation with the full exponents, how the exponents depend. So the full finite size scale picture that I showed you here, this picture here, and how they go down with L, this kind of slope, and this kind of slope, all this can be obtained exactly in this case. Yeah. Okay, but the detail is, of course, so that this is not necessarily a square lattice. So this was a triangular lattice. Okay, anyway. So is there any question up to here? Probably not. So finally, I'm close to my end, actually. So I would like to show you another curiosity. So up to now, I think that I've mostly closed the question of the watershed and of this explosive percolation. I would like to show you that one can also get another kind of transition in percolation. That's actually, again, a curiosity, which is hybrid. It means the combination of first and second order. And this is actually also analytic. It's not numeric, so it's analytic. So it's a model which is little constructed. It's a model, it's a mean field model, in which you say what we do is we have clusters, and we join clusters to form larger clusters. And you can organize your clusters according to your size. So you have here the small clusters, and here's the big clusters, okay? And then I say, in the whole philosophy, I would like to help the poor. Now, this is a very social system, so I will try to make the small clusters bigger, favor to make small clusters bigger. So in every kind of a marriage between between clusters, there must at least be one of them must be small. Yeah, so that I mix small and big maybe, but I mean, small clusters are always involved. And this fraction of how much, from where I choose what is small, what means small, this is a certain fraction of them. So the fraction of what means small, I call G, is the fraction of clusters which are most, let's say, yes, disconnected. Connected. And so, model, this is the model, yes, so I mean, this is only what you find. Of G, your transition will change. All this, I must admit. So if you have if G is 0, it means if you have no restrictions at all, then you have here the classical percolation. But the more you choose the G be a finite. G goes from this is when G is 1. This is when G is 1. I mean, everybody can be chosen. G is 1 means the full population is available for the second partner. And so it means that everybody can be connected to anybody. So G equals 1 means you have classical percolation situation. I mean, you just have no restrictions. This, the population that is forced to be connected to make it a smaller fraction of the entire population, then goes to the right sharp. Okay, this is what you observe numerically. And now you can very complex calculation, so it's mean field, so it's all analytical, and you can find that the order parameter, which I just behaves like this. You know, I mean, it's 1, 0 below TC, of course. I mean, always is the order parameter is 0 in one phase, but then it increases in that way, yes, where now the yeah, and the yes, and so there is a jump. There's a jump first, or a transition, and then there is a second order part, yes. And the cluster size distribution, tau, can also be calculated exactly, and it is a solution of this kind of equation. Just to give you an idea, I mean, what kind of calculations can be done. Okay, so what you see there is how dependent tau, the tau that I have here, this tau depends on G. So solving this equation is shown in the last one. This is how the equation then looks like. So tau becomes a continuous function of G, and also beta becomes a continuous. I mean, remember, all these taus are related to each other. Tau and beta are related to each other. In fact, when you remember that beta equals tau minus 2 minus tau over sigma. Ne? And so what you find is that we have a hybrid transition with an exponent beta that continuously changes with G. So this is an exotic phenomenon, but it can be proven rigorously that this is what happens. Okay, I don't know, I have some time still. Maybe I should stop here. I have more stuff, but I mean, maybe it's healthy to stop, no? ¿Ustedes qué dicen? ¿Cuánto faltan? ¿Con 5 minutos? Okay, let me. Well past the watershed. So this is why I show it. So remember you have a system with square lattice. Every side you have a number. We have on every side we put a number, 1. And then we side all these numbers along you get some value, and then you pass the smallest number. Okay? So this is also called the problem of the directed polymer, or the problem of whatever it is. That's and this now, yes, and now you do the following. And now what you do next is sides, more and more sides get blocked and torches. And then it can go. Also now prove exactly. See that, I mean, you have these, make it that this object, if you add the branches to the back, largest cluster. Yes, so here I show you now, oops, I show you now the fractal dimension of these three objects. This is now the fractal dimension of all the blocked sides. This is the fractal dimension of the crack plus the branches. And this is the fractal dimension of the crack without the branches. And what you see is that the crack without the branches has the fractal dimension of the watershed that can be proved. And then the branches, the extra branch part will go away when you increase the disorder. So this is the last thing here. What you can do is you can increase the disorder by increasing the difference between the numbers that you have. Finally, find a distribution which is distributed according to some power law, which is not normalizable anymore. In this way, you come to what is called the limit of infinite disorder. So if you, two definitions of what is the limit of infinite disorder, the simplest one to understand is that you say that the sum of all numbers is smaller than the next number. This is infinite disorder. Another definition of infinite disorder is that it's in the distribution is not anymore normalizable. Okay, so in this case, if you can construct them, it's not so easy because you have to always shift the cutoff. But when you construct them, then you can see that in infinite disorder, yes, here you find that the path, even the first path, is already watershed. So the paths are watershed fractals, and the crack itself is also the fractal, which is watershed. Okay, and so this I think. No, okay. A lot of stuff. Thank you very much. So, questions? Questions?
So by changing, you can change you can change continuously from a second order to a first order.
Oh.
By changing the Q of the hybrid model. So
no, the hybrid model is always both. It's both. Hybrid model is always a little first order and a little second order, both together. And the second order part changes continuously the exponent. But the jump is always there. Yes, but the jump also changes in way. So, see, yeah. Accessible
parameters in the correlated correlated surfaces. When we change the index or parameter, I think
it's the Hurst exponent.
Yes.
Yes.
I think it was the fractal dimension
changes. First quantum.
Yes.
Yes.
To vary kind of like in a mirror way, so the accessible.
Yes, they go like this. Yes.
Yes.
Yes. Yes.
Is that kind of like a regular thing for those kinds of? Is that a regular behavior for the fractal dimension, or is more of a coincidence in that case?
Well, you expect that it happens because you know that at the one end both are the same, and the other one you know the value, so it must go from there to there. I mean, but the question is, what happens in between? If in between the models follow also SLE or not? I mean, that there is a change of dimension. This is kind of trivial because you know the two endpoints, but you don't know what happens in between with the conformal invariance of the path. You know that each extreme is conformally invariant, but you don't know if the middle is. So this was the question that we tried to understand. Yeah.
And the other thing is when we have hybrid transitions.
Yes.
Do they always happen as you showed earlier with the Yes, with hybrid, are there many ways in which hybrid transitions can happen, or only in the way that you showed earlier?
You know what, usually it's like what I showed, that there is a first kind of continuous transition and then there is a jump. This is typically like hybrid transitions are look like this. Mhm. Okay? Ja, Ona, gut.
First of all, thank you for the talk. Have these ideas to look for a first order transition been applied in continuous percolation models? Would
No,
that make sense?
I don't think that we found any kind of thing like this, no.
Would maybe expect to find a first order transition in a continuous percolation model, or doesn't make sense?
Yes, it makes sense. I mean, you have to, in order to get a first order transition, you have to manipulate on the rule of connection. You have to decide what is forbidden. You have to make some extra, and I don't know, I don't see why it should not work also if you do the same kind of rule in the continuum. I mean, you can always say in the continuum, what is the bridge? It's easy to define, and you can then make a model like bridge percolation continuum. But I have never seen anybody doing that. Yeah.
Okay, thank you.
Question, no? Hola. Oh. So now we have the coffee break. 20 minutes.
Mhm. Aquí. ¿Qué pasó?
Es el mismo que está en el principio.
¿Cómo?
Ese es el que está en el principio.